What's up, fellas? In this video I'm going to show you how to prolong the life of your computer. This particular unit here has suffered the fate of thermal cycling. In this video we're going to look at something a lot of computer owners don't know that engineers are very well aware of, and it's called thermal cycling fatigue. And it's been discovered through testing that the joints on your CPU and GPU can withstand a thermal cycle period of roughly 1,200 to 1,600 thermal cycles before metal fatigue is observed in the solder joints. Because of the difference in coefficient of thermal expansion of the solder versus the steel pins, the coefficient of thermal expansion of solder is 29 times 10 to the power of negative 12, whereas the steel pins is 11 times 10 to the power of negative 12. So there's a significant difference, and as a result, this happens on your circuit board. I did a reflow on this particular unit and got it to work for about another month or two, but after that it failed again, and it looks like it's going to cost $500 for the motherboard. So being as old as it is, I probably won't fix it. If anyone's interested in this and wants it, just let me know. I'll see what we can do. It just needs a motherboard and a hard drive. I took the hard drive out of it, but it was a great computer before that. But I think you guys are going to like what you're going to learn. In essence, in short, don't turn your computer off if you think you're going to use it again within the next 24 hours. It's best to just always leave it on if you're not worried about power consumption, but make sure you dust it out occasionally. So there you have it. In this video, I wanted to show the effectiveness of using a cooling pad for anything that demands a lot of processing power out of your computer. I am currently, I don't know what you would call this, saving a video. It's already been edited and all that. I think it's, I'm not sure the actual technical term for what the computer is actually doing to this video. It's encoding it, it's saving it, it's making it compatible with other formats in some way, I guess. I don't know what it's doing to it, but it requires a hell of a lot of processing power. Both CPUs are maxed out. And the temperature of my computer is 194 degrees, which is a little scary. So I'm going to go ahead and throw this heating pad on there real quick, just to kind of show how much they do actually help. And I want to talk about why this is so important. A lot of people think it's okay to let their computer just get as hot as it needs to. But the reality of the matter is, a lot of the pins connecting your CPU to the motherboard, and the GPU for that matter, have a little bit of a problem. They're in conflict with the solder at temperatures of this range. The coefficient of thermal expansion of the pins is different from that of the solder. So you're getting forces built up inside of those pins. And as a result, over time, microscopic cracks that can only be viewed with X-ray take place. And they are the actual failure of most computers. Have you ever heard the term reflow? The reason for a reflow is to resolder these microscopic cracks that separate the pins from the solder joint itself. Over time, the pin terminals grow and contract at a different rate than the CPU itself, or than the solder joints itself, is what I meant to say. So because the pin is expanding and contracting with more force and more distance than the solder, over time they separate from each other on a microscopic level that you cannot see, that becomes very problematic. It conducts electricity, but not the way it's supposed to, not the way it used to. As you can see, we're already losing quite a bit of temperature there with just this cheapo little cooling pad. I'm not even sure I'm on there right. Anyway, technicians discovered that it is best to leave your computer on all the time and never turn it off. That is, provided you maintain it, keeping the dust out of it, than to turn it off all the time. If you leave it running all the time, you don't expose it to the high thermal contraction and expansions that it sees when you turn it off and on all the time. So if you just leave it running constantly, it's never exposed to that thermal shock. They say it is actually better to leave expensive computers on, like computer servers in businesses and stuff. They never turn those off for more reasons than just to keep it up and running. It's actually better on the system, lifespan wise, to leave it on. If you've got a $100,000 computer and you find out turning it on and off every day could reduce its lifespan by 5 years, you'd be inclined to leave it on every day, all day. So as you can see, I'm now down to 176 degrees, and the solder pins, or the solder joints on my CPU and GPU pins, are loving me for this. And this computer will last a lot longer if I maintain the habit of doing this. This thing's going to run like this for a while. As you can see, this very slow process of editing this video. If anyone knows what this process is called, please let me know. Is this called formatting? Is this thing formatting the video? Is that what it is? After you've edited a video and stitched it together? I don't know. Compiling? Who knows? All I do know is that I, a long time ago, studied this about computers and was brought to the conclusion it's better to leave your computer on all the time versus turn it off. But you gotta clean it. You have to dust it if you're gonna do that. So don't take one part of my advice and not the other. I tend to leave mine on quite a bit. I still turn them on and off all the time, but I can corroborate the heat shock thing because I took my computer to work one day when we were working at a Menards to go through hundreds of pictures that we needed to examine. And it was sub-zero temperatures that day. Well, lo and behold, the next day my computer didn't work again. The GPU had failed. And I did a reflow and it worked again. However, that reflow was done by me and it was not done well. So eventually it did fail again, but it corroborated what these gentlemen were trying to share with us. And that is, do not let your computer get excessively hot. 190 degrees is not acceptable under any circumstances. I don't like the fact that it's at 174. I would prefer it never got above 130 degrees, personally. I mean, anything that's too hot to touch, in my opinion, is reducing the lifespan of my computer. So 130 degrees is about the upper limits of what you can touch with your hand. At any rate, I just wanted to share that with you guys. You definitely need to keep these computers cooled down if you want them to last a long time. Maybe one day I'll draw up an actual diagram that shows the actual mathematical formulas that's used and the actual forces involved. I want to say the forces are only on the order of a couple hundred pounds because of the small cross-sectional area of the terminal pins of the CPU. I'm pretty sure the cross-sectional area played a large key role in those formulas. It's been 5-6 years since I've touched them, but expanding and contracting metal produces tremendous amounts of force. Tens of thousands of pounds is very common in these equations. So 100,000 pounds is common in railroad track equations. The gap they leave in railroad tracks is left there. And if you don't leave that gap, forces in excess of 100,000 pounds can be seen in a railroad track. So there you have it. Just wanted to share that with you guys. Over the course of me yapping, we lost almost 25 degrees there. Well, about 15 to 10, but I think we were at 190 or something. Definitely feeling better about it. The fan has reduced speed, which I hate that. It kind of pisses me off that I can't get inside my computer and decide how fast I want my fan to go. I want it on full speed. I do not want my computer idling at 174 degrees. So if anyone knows how to hack into the fan, I've already looked online and went through the tutorials. This thing just won't let me into it. There's just no prompt that gives you access that deep into the system. But if anyone knows how to do that, like in command prompt or something, share that with me. Because this fan can go faster than this. I don't know if you can hear that. At any rate, there you have it. Definitely a good idea to use a cooling pad when you are formatting a video or whatever this is called. Help me out here if you're a techie. What am I trying to say? What is this thing doing to this video? Is it formatting it? Is it stitching it together? Like, I don't know. I want to know what that word is. Anyway, thanks, fellas. Your comments have been a big help lately. I've been getting some really good comments from some very intelligent people, and it makes this worthwhile. In the beginning, I was getting an awful lot of jackassery, and it just makes it a pain in the neck. And I'd ask myself, why am I doing this at times? If that's the type of comments I'm going to get. But lately, I've been getting a really good flow of really smart people with very helpful comments. And other viewers of my videos read your comments, guys. So you're not just helping me out. I also view comments when I'm looking for information to see what people have to say. It's a tremendous source of information. It's not always right, but you can kind of tell when you found a gem. I mean, at least you have something to look into. You find something to look into that way, you know. So at any rate, I'm shutting up. There we have it. Looks like we're stuck at 172 degrees here. It's not going below that mark. I'm not sure why one CPU is cooler than the other either. Perhaps just the metal. Maybe it's on a different side of the CPU because the metal conduit is kind of going away from the CPU in one direction to where the left versus the right side would be the hotter zone. Alright, I'm shutting up now. I'll holler at you later, fellas. Alright, fellas, I said I wouldn't do this, but I dug out some very old math books of mine. These things are so important to me. I've designed a lot of machines with these. This is out of a book I used to have that I went ahead and made copies of. But anyway, you remember when I mentioned the amount of force a railroad track can experience in summertime is 100,000 pounds of force? I'm just kind of glad that for once I freaking remembered something. I was right. I'm not bragging here. I just wanted to corroborate because I've been making an effort, guys, to when I spout things off at the mouth, I want to be damn sure I'm giving you guys the accurate 100% truth. That is very important. There is so much misinformation on YouTube and stuff like that, and guys will just say anything without even checking their facts, and frankly, I'm sick of it. So to me, you know, as a content creator, it's very important to me that the information I provide is true and accurate. And sure enough, here's the equations that I learned many years ago. This describes a piece of steel track 20 meters long that experienced a temperature change of 45 degrees Celsius from winter to summer, okay? Because no expansion was left in this track, using this formula, which I am very fluent with and is a very amazing formula. I used this to develop some heat engines that turned out to cost way too much and not last long enough, but that's neither here or there. But at any rate, the force you get is in newtons, so you have to convert it to pounds. But yeah, a piece of railroad track will produce 100,000 pounds of force. So let me give you a quick illustration of what's going on a circuit board, fellas, when it gets hot and cold. First of all, thermal cycling of materials has a limit. A lot of the specifications that I've seen for common materials is 10,000 cycles. 10,000 thermal cycles before metal fatigue will start to bear its ugly head. So we're going to keep that in mind for a second. Not to mention, let's look at a situation we have here with a pin from a circuit board. This is a microprocessor or any circuit on a circuit board. This is the circuit board itself, and this is the solder joint. This is a cross section, okay? And this right here is the copper conductor or the laminate of the circuit board that's been left behind from the etching process. Now what happens is every time your computer turns on, this section right here has a bit of an issue. We have soldered to a steel pin that's connected to a circuit board here, okay? Now, of course, this is probably some kind of alloy. I don't know what type of alloy that is. I'll look into that, but take a look at this right here. This is the equation used to determine the rate of thermal expansion based on a certain temperature junction. Now, we saw my computer go from room temperature of 70 degrees to 194 degrees. That's a substantial temperature jump, okay? Right here I have wrote down the coefficient of thermal expansion of lead, which is 29 times 10 to the power of -6, which is like some weird number like 0.12345 29. That means, my bad fellas, I'm a little rusty on the math. I haven't touched a calculator in over 5 years. That is 10 or 29 times 10 to the power of -6. There's 6 significant figures behind the decimal. I'm a dumbass. I don't know why I did that. Here I am talking about providing facts, and something in the back of my mind was telling me you're wrong. There's not 6 zeros. It's 6 significant figures. So that is that number. And there you have it. So, but that's just a coefficient. You have to multiply that by stuff. So that's, you got to multiply that by the length you already have and by the change in temperature. So that adds up. But at any rate, look at this number here. Lead is 29 times 10 to the power of -6, whereas iron is 11. We have a huge difference there. That's a difference of 18. Okay, and there are some metals whose coefficient of expansion is, brass, for instance, is 19. So that's a huge fluctuation. And what that does is causes a force in this area, okay? This pin grows less than the solder. So the solder is attempting to move farther than the steel pin. Now in the middle here, everything kind of centers out like this. It'll kind of grow like that because just the way things, because it's going to be in the center of the solder joint. That's where the epicenter of the issue is going to be. So if this pin grows at a slower rate than the solder, that solder is putting stresses on the contact point right here. In addition to that, if this area here in between the circuit board grows more than the circuit board, now we have a microscopic scenario in where the solder joint itself wants to lift off the board because of this space in here. We'll call this L2, L sub 2, which would be this distance. So we've got this microscopic liftoff, which I've exaggerated here because of that growing. So it wants to grow off of this conductor pin here. So let's say if we blew that up again, there would be a little gap right there, and here's the metal. So the computer heats up and starts acting weird, and we don't know why. It's because this little space here has grown and shrank so many times, and the coefficient of expansion of this material, of the circuit board, I guarantee you, is almost nothing compared to metal. Materials like that do not expand and contract. So there is a huge area, a huge issue right there. And what happens is they say microscopic cracks that can only be observed with x-rays take place here and along this surface area here on your circuit board. There's a lot of literature online about this, guys. An old computer programmer told me about how in his firm they would leave their computers on 24/7 because it was cheaper, because you got a couple more years out of like a $10,000 server if you left it on all the time. Now you got to do your maintenance, you got to dust it out. I've said that like 5 times already, but at any rate, I'm not going to dig any deeper into this because a lot of you guys have probably already lost you. This is just pretty deep, unless you're like really enthused about just interesting things like this. But if you're a computer owner and things like that, and you're concerned about the lifespan of your expensive computer, that right there, guys, is where most of the problem comes from, and the separation of the pin and the solder. The pin doesn't grow as much as the solder, so eventually they separate, and it's on a microscopic level that can only be seen with x-rays, which results in voltage fluctuations. You'll still get current passing through there, but it's not going to be the right current. It's going to act weird. Some strange things can happen. Maybe even capacitance. I don't know the whole story, but something weird happens between that interface that no longer allows it to conduct electricity in a way that enables the computer to function properly. I know this to be a fact also because I once took my computer out in the wintertime and it subsequently failed that next day, and a reflow solved the problem. So what a reflow does is remelts this hat back down to the copper. Fellas, I'm beating this dog to death, but I got to show you this. I found some very interesting information on the subject. Probably not going to bother posting this link. I just don't have any time, guys. This is about fatigue of the lives of solder joints. Decrease with component weight increase. The solder joint lives calculated by FEA were between 1,300 and 1,600 cycles, which agreed well with experimental results. So what this is saying, guys, is if you turn your computer on and off 1,600 times, you're going to start seeing metal fatigue in the solder joints. Let's do a quick calculation here. You turn it off and on every day, so man, that's not very long at all. Now this probably depends on how hot you let it get, of course. 1,600. About 4.5 years is the typical life expectancy of a computer solder joints. This is actually getting pretty interesting, fellas. I've found some new literature that was not available the first time I visited this topic. Look at that. These are actual failed solder joints from what we've discussed there. I'm half tempted to go ahead and do the math for you guys and tell you what the forces involved actually are. I fear no one would bother waste the time watching this. Maybe I should just go ahead and do it. You see this interface right here, fellas? See how that's a black line? You should not see a black line right there. That's a failed joint. That interface is where that stretching I was telling you about is going on. Right here is where the solder joint interface is also here. And this line you see right here is the copper on the PCB. This right here is the actual circuit board itself. But this particular, I'll probably leave a link in the description for you guys on this one. This particular piece of literature is very extensive. You can see some tearaway action there. See how that just kind of, those joints are tearing away. On the macroscopic level, things aren't what they seem. Now this is the one I was telling you guys about. That's so cool, they actually have pictures of what I was saying. This separation here, this piece will grow up and lift off right there, because the expansion rate of that solder joint is higher, so you get a separation right in there. The expansion rate of the solder joint is higher than the PCB is what I'm trying to say. My nomenclature is just not prepared for this discussion, and I apologize for that. Here it is. This is the, man, that is so cool. I'm gonna admit that I was being somewhat speculative about this particular failure mode. It just dawned on me that's probably what was happening. The failure mode I read about back in Scientific America 12 years ago only discussed this failure mode, but it's obvious that would happen. That's actually being corroborated with these particular photos here. That's the separation caused by the expansion coefficient difference between the PCB and the solder itself. Okay, that has nothing to do with the pin. The pin is this other interface right here between the pin. This here is the other issue, where we're still connected to the copper on the PCB, but we separate from the pin. Whereas this is an instance in where we've separated the solder joint from the PCB, or the copper that's on it. This goes into very in-depth. The reason why I'm reluctant to do the formulas on this is because determining the actual size is going to be a bit of a pain. But I'll tell you what, I'll go ahead and grab a circuit board, a micrometer, and I will tell you how much force is actually induced from that lead, how much pull-away force it has, and then what the force difference is between the solder and the pin. Okay, fellas, so in conclusion, this is the force that we're dealing with here in newtons, which is so small. But after you have the force, you then have to calculate the pascals, because the force doesn't tell you much. Let me give you an example. Back when the commercial airline industry first started to take off, engineers were perplexed with the problem of how to stop women's high heels from poking through the deck of the airplane. They were popping holes in the floor of the airplane because the pascals of the point of that high heel are so high, the aluminum honeycomb structure couldn't withstand the force. So when you have a force subjected to something, you also have to understand the pascals. The pascals takes into consideration the area the force is acting on. Let me give you an example. This force may not seem like a much, but if you said, you know what, that's not a lot of force, and I said, okay, well, let me take a needle and stab you in the eye with this needle with a force of 0.0 or 8.6 to the power of -12 pascals. You probably wouldn't let me stab you in the eye with a force of 8.6 to the power of -12 pascals. It's not a lot of force, but the area we're working with was extremely small. So you have to take into consideration the needle concept. We're not trying to press a tree stump through a wall here. We're talking about stabbing a needle through a piece of saran wrap or aluminum foil. It's a very complex situation we have going on here, but despite all that, it appears to me that the forces involved in this system are non-consequential, meaning that it is in fact nearly an attribute of the thermal cycling fatigue that I mentioned earlier. And as I said, because I've designed a lot of heat engines, I've discovered that thermal cycling is actually a devastating behavior on machinery. You don't come back from thermal cycling. There is just unrepairable damage is done to the crystal lattice of the metal structure itself. It is, in this particular case, 1,300 or 1,200 to 1,600 cycles, I think they said, before you start seeing metal fatigue in the pins on your circuit board. So, long story short, it is in fact better to leave your computer on 24 hours a day, 7 days a week. If you're not worried about wasting a little bit of electricity, I definitely, after reading some of this literature, have taken this information into account. If I'm going to be using my computer later on that day, I certainly never turn it off. If I know I'm not going to be using it for a few days, yeah, I'll turn it off. But this off and on stuff, and not using a cooling pad when you're formatting video, is a huge mistake. So anyway, now that I'm done boring the hell out of you, by the way, if you manage to make it through all this, you are a freaking champion. Not a lot of people are going to sit here and watch this kind of stuff, but I promise you it's within reasonable accuracy. I mean, I did take the time to figure out, the numbers are so damn small, it's a real pain in the ass. But in conclusion, as I said, the forces we're working with here appear to be non-consequential. Non-consequential. I can't talk today. But elastic constants are the figures that I use to determine these forces and attributes of this system. Anyone has any input on this, just let me know. How important is this video? This is a really nice computer right here that failed due to thermal cycling. Needs a new motherboard that costs about 500 bucks. A reflow was done that lasted a little while, then it failed. But for the most part, this is what happens when you take your computer into sub-zero temperatures after it's already a few years old. I know for a fact that's what killed it. It's no coincidence, and it was about around the 4-year period, so right around that 1,600 cycles. So you'll get about 4.5 years out of a computer if you turn it off and on every day. That's their estimation based on the strength of solder joints. So definitely a cool little subject. Hope you guys like that. Maybe we'll use this for the screenshot.